Okay, good afternoon everyone and good day for all of you who come from region, other region. So welcome back to RoboCup at Home Education online classroom, and today we have this special invited lecture series who we invite teams from our previous online challenge to share with us some of their experience and also development during the development for the competition. Okay, so we are very proud today that we have this our speaker Danny from UTAR, Malaysia, for the topic simulation of service robot in Gazebo. Okay, so let me switch this thing. Okay, so this is the arrangement. So today I will again be the host. I'm Jeffrey from RoboCup at Home Education, and today we have our speaker from University Tunku Abdul Rahman, Danny Ng Kiat as our guest speaker, and the time. Okay, so we will start from 3 and we will end before 5 for time zone GMT plus 8, and also for people that come from other places. That should be the timing. So I hope you enjoy, and also this time is suitable for your timing, hopefully. Right, maybe not very good timing for people in US, but let's see. Okay, if anyone from the US will join today. And for all other information regarding this today lecture, you can find it from our website. So the link is over there. You can head to our website, which is the page that you sign up. You can find other information, including the slides and also the videos that we are going to share after the class. All right. So finally, as a privacy reminder, I'm currently recording this session. So the whole session will be recorded, and later on will be posted on our YouTube channel, and will share in our all our social media channel. Okay, so please be careful on your privacy. Please don't turn on your webcam and also your mic if you are not presenting, unless during Q&A, which we allow you to actually interact with our guests. Then during that time, yes, you are free to do so. But yeah, but once you share, which means like you agree for us to actually share your information online, right? So that is the agreement. We didn't really sign the media release form with you, but that is the agreement that we mentioned to you first over here. Okay, so I hope everyone understands this. Okay, so as usual, let me briefly explain or introduce RoboCup at Home Education to especially for guests who are not joining or haven't, or this is the first time that you're joining this activity. So we are RoboCup at Home Education, and it's an educational initiative in RoboCup at Home, which is in RoboCup, that promotes educational effort to boost our participation, which is our competition participation, and also to promote this artificial intelligence focused service robot development. So currently we have 4 active operation under this initiative. So for the first one is we organize education challenge, which is the educational version of RoboCup challenge for at home. And we do it for national level, regional, and also international level. But this year, we actually switched everything to online. So last month, or the month before, we actually conducted our first ever online challenge. So for you who are interested in our challenges event, feel free to look at the content that we have opened up and share on our website and also our social media channel. Okay. So the next thing that we focus on in this initiative is we gather resources for this open source educational robot platform. So which means we gather all the learning resources to assist our community to learn how to build service robot. Okay, not just for the competition, but you can learn it for if you want to learn about AI and also robotics, for your computer science courses, for your engineering courses. Yeah, so we have a lot of materials inside there, and not just having all the resources for learning. For example, like we have all the source code, we have all the tutorial, but also we try to put everything into an open courseware. So we actually have curriculum, and also we have the learning courses that you can actually head to our learn page on our website. So that is our third operation. which is we generate a lot of learning materials on our website. So feel free to look at our website for more information. And lastly, over here, I would like to promote as well. So if let's say you think that all these materials are very useful for your community, feel free to contact us, because we have this outreach program efforts that we try to bring all these resources to your community. So we would like to share everything that we open up for the public and try to see how all these materials can facilitate the development in your local community. And particularly now we can do everything online, so things is getting much easier now. So feel free to contact us. So for more information, go to our web for all the information, including all the media. You want to find the video or all the resources, for example, the slides, the learning material, and so on. Everything is are posted on our website. And if you want to interact with us, feel free to join our Facebook page. Okay, and within the Facebook page itself, we have a Facebook group, which is you can join us as a member and also interact with us. You can send us a message or you can post something, and yeah, all the community will be interact inside that Facebook group. Okay, so lastly, I would like to say thanks on behalf of RoboCup at Home Education Initiative to all our sponsors. So we put all the logos over there. So these sponsors have been helping us since the very beginning until now in all these activities. Okay, then a brief introduction about what is this online classes. So we have previously online classes to facilitate teams to join the competition, but after this, since now it's after the competition, so we have this invited lecture series, which we invite teams from the competition and also various experts within our community. So we have many professors and also engineers within our communities that they have some expertise that they will share with all our community in this invited lecture series. So we have conducted quite a number, so you can go to our online classes page to check the previous one. So all the videos and also the source code, if let's say they open source. I think today Danny will also share the materials with all of you, so feel free to check out. And also we have more this online classroom coming, okay, later on, so please feel free to see which one you're interested to sign up and also join us. Okay, and we have this regular online classroom track, which is we have introduction to service robot, a full 6-week online classroom that you can actually take up and go through the content anytime using your own pace, right? And also not forget the special online challenge track, that these are the materials that we use to share with our sorry, I need to admit someone. Okay, it's admitted. Right, to share with our community so that they can do some development for the competition. Right, so for more details, please head to our website to check out the details. Right, okay, so now let me once again introduce you our speaker for today. So Danny Ng from University of Tunku Abdul Rahman, Malaysia. So Danny Ng received the Bachelor of Engineering degree in Electronics Engineering from Multimedia University in Malaysia in 2008, and then for Master of Engineering Science degree from UTAR, right, in 2012. So his research interest includes the development of indoor robots, SLAM-based navigation, microcontroller system, and robotics application. So this is just a very brief introduction about the speaker. So I'll pass the mic to our speaker today. So Danny, you can introduce yourself more to the audience, and you are invited to start your talk today.
So let me just share my screen first.
Okay, so let me turn off. Okay, so the mic is yours.
Okay, thank you, Jeffrey.
Welcome.
So let me just okay. Can you all see my screen?
Yep, I can see.
Okay, good. I think first of all, good afternoon, everyone. So thank you for inviting our team lah. So I'll be representing our team to actually give this short sharing about, first is about our team, itself, how we started, and we will actually go into how we actually work on the robot. Actually, in the slides later on, you will see that we actually built physical robots, for the at home category itself. But I think due to the virus itself, we actually started the simulation part for the robot also. So now, let me just start this. So let's just try this for a bit, because I think I can't see the chat from my side. So if you have any question that you want to leave, you can always go to this link over here. If you can see the link on top over here, so you can actually go to the link, and if you actually drop some notes or something, then maybe I can answer it later on once. So any question that you drop in the link will appear over here. So because I think it's hard when I'm actually presenting, and it's a bit hard for you to actually turn on the mic and speak. So just drop your question in the link chat over here. So at least we can go back to the question once we actually reach the break or reach the end of the Q&A section. So a bit about what I'm going to cover today. I'm actually going to introduce our team itself, how we actually get started with the RoboCup, and also with events with RoboCup at home education. I will actually share how we actually create our simulated robot. Hopefully, I will go by sharing can actually help you, to create, your own robot in simulation itself. We'll go through some basics such as interfacing with sensors. We also look at like how do we create actors in Gazebo, and actually use different scenes and objects that's available, open source and available out there in the public, that we can use to help us when we are actually developing developing robot in the simulated environment. At the end also, I will share with you like a very simple laser-based object follower. Called object follower. It can be anything that is near the robot. The robot will actually track and follow it. So now let's start with our team itself. Myself, I'm actually attached to the university in Malaysia, University Tunku Abdul Rahman. For those that are from Malaysia, I think you all will know it. So I'm a lecturer over there, and we have a team of currently a team of 5 students working on this project itself, undergraduate and also postgraduate students. So I think I first got to know about RoboCup was in 2017, if I'm not mistaken, when I first met Jeffrey. So I think from there we actually started and to actually to have like RoboCup and RoboCup related events in Malaysia, and also from our side itself, to join and participate in RoboCup event. So I think the first official event that we joined is actually in Japan in 2018. I think this photo over here is the 5 of us that started to work on projects related to RoboCup. Those are this photo is actually taken in Japan during our workshop in QTech in 2018. I think in that workshop itself, we worked with Turtlebot, and from there we actually get to know, you know, a lot of how to do certain tasks, to do completion of tasks, to actually work on different libraries that you can actually work with, you know, when you're dealing with things like ROS and things like that. So after the at-home service robot manufacturing workshop, we come back to Malaysia and we actually started our own, you know, robot development team. In our university itself, because previously we participated in a lot of other, I would say, more precision or more automation-based robotic competition. That's why we actually have a lot of materials laying around. So we actually have to utilize all those materials that we have to build our own robot. So I think after that, I think we have like 3 students that participate in the RoboCup at Home Education Challenge at KRASF. That is in last year, end of last year. You know, Jeffrey hosted the competition there at KRASF, and we have a group of students actually participate in that competition. And I think recently also we participate in the at Home Education Challenge last month. We were supposed to have a joint team with Kiat in May, but the competition was cancelled due to the coronavirus. So on our side itself, we actually started the development. These are the robot platform that we have created. Still, I would say our team is still quite new, and we are actually utilizing whatever material that we have to actually build it up. So there are a lot of things that we actually have to work on ourselves on our side. So we also have created some basic libraries to control like the robot base that we already own, and to interface all those you know, all the libraries and all the controls algorithm together in the system itself. So based on this, when we actually wanted to develop our simulation model, we actually have to base it on the robot that we have developed. So I think in this sharing itself, what I'm going to share with you is some of the, I would say, key takeaway from our experience when we are building our own simulation, what we should actually focus on, and how should we, you know, what are the key parameters like when you are actually designing your own robot in simulation in Gazebo itself. So well, for the development of service robot, there are a lot of things that is available. I think one thing that Jeffrey shared at the start of the sharing today is there's a online open courseware. So I hope that everyone here can go and have a look at it. There are a lot of resources there to get you actually started with, you know, running ROS and running all the basic libraries and giving you all the basic concepts that you need before moving into like a more complete development, or, you know, going into like building your own robot in simulation itself. So it is important to get yourself familiar with ROS and how it actually works. So how are the file structure, how is the libraries, how do you actually install new libraries, how do you link libraries to your project. So I would not be covering all those today. I will just straight away go to the Gazebo part. So if you are not familiar with that, I would recommend you to go through the OpenCourseware and also go through the tutorials on ROS itself. Those actually helps a lot when it comes to the the development part of simulation. Now, for the service robot, simulated service robot that we have, we are actually using Ubuntu 18.04. So we are actually running ROS Melodic on for our simulation. Now, this is also one thing that I would like to recommend you all to look up. That is the tutorial for Gazebo itself. So the tutorial for Gazebo will actually give you all the installation, all the installation steps that is required for you to run Gazebo on your PC itself. So to actually use I'll be sharing my codes that I will be demoing to you in this session later on. At the last slide, you will be able to see the link to the code. So to run the code itself, you need to actually install the Gazebo as according to what is stated in this link itself. So let's move towards the first part of my sharing itself, is what we should actually pay attention to when we are creating our own robot. So now, one thing that we need to take note of is when we create our own robot, first is we actually need to understand what is the description language and what is the robot description file use and macro language used in Gazebo itself. So to actually create a robot in Gazebo, you actually use something called a URDF file itself. It's actually a XML format that is used to represent a robot model itself. There's only two things inside it. One is actually a description of your model, and another one is description of sensors. So based on these two items itself, you can actually describe most of the robot that you will actually see. So there's also a macro language that will help shorten your code itself. So it's actually called the XML macro, the Sacro language. So I'll be using these two to describe the robot you see in the picture before. So a few slides back, I think you have seen the robot that we have developed. So over here, I'm going to share with you the robot that we have developed also. Let me just run it. So hope everyone can see my screen over here. This is the robot that we have developed for simulation. If you notice, this is actually an earlier version of our robot, the first version. Let me just go back to slides. So this one is the latest version of our robot, which we have a bigger frame over here. The initial robot was just a square base with a camera mount at the back. So what you have seen, what you are seeing over here is the older version of our robot, where we have laser for navigation, our square rectangular base itself, and then the depth camera shown over here. So now, to build this robot, we actually uses the URDF the description file itself. So let me just move it over here. So if you look at the robot itself, it is just a description of like different shapes itself. So for our robot over here, you can see that at the bottom, you will have one rectangle base over here. This is our base or the body of the robot. Then we have 4 wheels. So 2 of it, we actually have the driving wheels over here, and then we have our free wheel behind, and then we have the frame for the camera. So when you actually describe a robot in using URDF for Gazebo, every robot is actually represented through this. You have your base link itself that represent the this center or the origin of the robot itself. Then from there, you have different links. So if you look at the robot, we have the center rectangle base over here. That's linked. To develop a robot like this, I will just share the code itself. If you are not sure about what I'm explaining here, you can always drop me a question inside this slide. If you have any queries. So if you are actually building your robot itself, you always start with the base link. So the base of the robot itself. So let me just put this here. So you always start with the base link itself. So if you notice over here, what we have is just a rectangular base. So you can define your visual on how you want the, what is the shape, what is the, they have a lot of basic shape that you can use. So for example, over here, I've declared a box of, of the size of my robot. So you can see it over here on this side. So once you have designed this size itself, you can actually attach the different parts of the robots in. So once you have a base link, you can put your wheels in, you can put your sensors in, over here. So now, when you are working with the robot itself, there are quite a number of parameters, or there are quite a number of shape and sizes that you want to put in. But actually, based on some of the things that I want to share over here is when you are building your own robot for simulation, try to simplify some parts of your robot if possible. If you notice in our robot picture, let's go back to that. Our base over here is actually hollow with quite a number of electronic components and things inside. So when we are working on the simulation itself, we actually simplify that part into a rectangular solid base. So this will actually help, in simplifying it. As long as you specify the correct inertia tensor for the robot itself. So because Gazebo itself actually run physics simulation, so things like weight of your robot will actually affect the simulated output. So, for example, over here, when we actually build the robot itself, we need to make sure that the center of mass, is almost accurate and almost similar to the real robot itself. That's why when we actually created this itself, we need to specify the weight of the robot, and also we need to actually calculate the inertia tensor for the object itself. So calculation of inertia tensor is actually quite straightforward. You can find the equation online, and you should be able to calculate it according to the size that's needed for your robot. So once you have built your robot, right, it is important to make sure that the inertia is correct. Because if the inertia is not correct, then your robot might behave weirdly. Sometimes your robot might vibrate without any reason or things like that. So if you're building your own robot for simulation, make sure you get the inertia correct. So there is a tool over here in Gazebo that will help you with the view. So if you turn on the inertia itself, you can see the inertia of the system that you created. So if you notice, I'm not sure whether it's clear on your side, but if you zoom in over here, you can see the wheel actually having its own inertia frame itself, and the body is actually having an inertia frame. If you notice, the inertia is slightly slanted this way. This is because the base length and the frame itself is calculated as one object. So you will see that it's slightly slanted to the backwards due to the frame that's holding the camera over here. So now this is one part of it. So usually I would recommend you to simplify some part of your robot, but there are some parts that you can't actually simplify it. Like for our base, we can make it rectangle, but when we actually attach sensors and things like that on it, it will actually have certain shape or certain size. So for inertia tensor, is actually quite easy for you to calculate for standard shape like cylinder, a box, or sphere. But for things like sensors, like the LiDAR sensors over here, which is not a uniform shape, it's a bit hard to calculate on your own. But there's an open source tool called MeshLab that can actually help you with calculating the inertia tensor for odd shape like this. As long as you have the mesh for it, you'll be able to calculate the inertia tensor that you need to put in for the simulation. So for these parts itself, I think there are a lot of CAD drawing from the supplier itself. So you can actually import this into the robot description file. So over here in URDF file, for this simulation itself, they actually take in the Collada file, the .dae file itself. So if you can export your model to a DAE file, you will be able to import it in the design. So this way, you can actually import the sensors, different type of sensors itself. But one thing to take note, for this part of URDF file, it only imports the shapes and also the outlook for the mesh for the objects that you put in, but it does not give the functionality of a sensor. So to actually create the sensors function in Gazebo itself, you need to add there are lists of plugins that's given by Gazebo that you can use to create all this add functionality to the sensors itself. So if you can see over here, let me just close all this. I've added 3 sensors to the simulation. One is the laser sensor, another one is the IMU unit itself, and the last one is the camera. So if you go to this link itself, you will be able to get the full list of sensors plugin that you can include in your robot. So you can also, if you visit the website, you can notice that you can actually change quite a number of parameters within the sensor itself. So for example, if you're like my robot over here that we use, we are actually using a 270-degree Hokuyo laser sensor. So with this laser sensor, there are certain area that we can measure. So we actually need to key in all these meters. So this 4 meters. And once you actually have configured the parameter files for your sensors, for your drive view itself, then we can actually launch the robot model that we develop. So once you launch the robot model you develop, you will get something like this. Let me just make it. Okay. So you will get a robot that you describe in the description file. So in an empty world itself. So I hope that maybe after this you can run through the basic Gazebo tutorial. So inside there, it will actually tell you, how to launch empty world itself. So over here, we have a totally empty world with our robot in the middle. Now at this point itself, what Gazebo have been created is, let me just turn this back on. So when you actually have all these sensor inputted into Gazebo, you can actually get their output through ROS. So if you follow the installation step that's given in slide 8, you will be able to launch the Gazebo Notes bridge itself. So with the Gazebo Notes bridge itself, you can actually get access to all these topics over here that's published by the robot. So you actually have your camera, you have your camera images, you have all the joint state over here. So if I share the RVs with you, you will see that you have the robot over here. Now, this is the robot description that we have, with the views, with the camera itself, And you can actually see the camera view over here at the bottom left, and you can see the depth sensor view. So if I import an object into Gazebo, you can see it reflected in this view itself. So let me just put screen here. So you can see a robot over here. If I put a sphere over here, you can see that, you know, it's reflected in this depth map itself. This is a depth view by the robot through ROS. If I move this around, you can see it change in the camera view. So with this, you will be able to interact with the robot over here. So this is how you put in the sensors, and you can interface with the robot itself. So once you have the Gazebo ROS plugin, then you can actually have, you know, all these notes over here, where they actually publish topic that is related to, you know, the output from the simulated environment. So for this simulation itself, it works both ways. So it actually publishes all the sensor data out. You can also send, you know, control signal in. So back to this robot itself. Let me just bring up the robot screen again. So we could also control the robot through the command velocity. So we can actually drive the robot around. So let me just set up the robot steering itself. So the topic for robot steering in my example is this drive controller. So not sure whether you can see it moving. Let me just zoom in a bit so it's larger. So once I've set up the robot steering over here, I can actually move the robot around, if you can see it. So I can actually drive the robot around, you know, using the controls over here. Now, once you have this few things set up, you actually have what we call a basic setup for simulation. You can use this simulated environment with a lot of, you know, actually with most of the example that is available out there for ROS. Because with this itself, what you have is actually a functioning robot itself. But one thing to take note, if you notice on the camera screen over here, there's always something blinking. This one is actually due to the simulation issue. If you actually turn off the TF view over, if you notice in Aris over here, there's a TF link. Once you turn it off, then it will go missing. So it is just due to the view in Aris itself. So with this, you are able to control a robot. I think if you have done ROS tutorial, there's a turtle simulation. So this is what is almost similar to that, but with a more complete robot with camera and also the laser sensors. Just notice I did not which lies the laser sensor. So if you notice over here, you have your depth camera, and also you have your laser sensor readings. So by having set up the URDF description, you will be able to simulate a basic robot in Gazebo itself. So that is for this one. Let me just open this. So you have your RVs over here. You can actually control your robot on the steering itself. So I think let me move on to the next one. For the next two sessions is I'm going to share with you how we create our environment. And also at the end, I'll show you one example for the simple task that we created a code for. The code is created quite some time ago, so not the exact one that we use for the competition, but it's something simple to showcase to you on how we can actually use this simulation to develop robot controls. So I think based on the schedule, we'll take a short break for now before we continue again. At this point, any question or anything that you are not sure of?
Right, thanks Danny. So maybe I can do some interaction for the Q&A. So maybe it's a bit hard. I'm not sure because I didn't receive any question from the audience from here. I'm not sure about your side. So is there
no
any
question also from my side?
Okay, but I have some question regarding what you just presented just now. So maybe we can share with the audience. So just now you're talking about how we create the URDF and also some definition to define the functionality, right?
Yep.
So we have a link, we have a join, and then we have sensors, right?
Yep.
Maybe you want to talk a little bit about also the shapes. For example, if I'm not mistaken, actually they have two types. For example, if we just want to do things in ROS, we actually don't really care about the shape itself. We just need to know the geometry, right?
Yes,
we know all the point. But let's say if we want to do collision avoidance, for example.
Yes.
So the shape actually important because you have a rounder shape or a sharp shape, then that's different. So from my understanding, because I don't really work a lot in Gazebo, but from what my understanding, especially when we deal with navigation, so we need to know the shape which is defined in the Gazebo format, which is a bit different from URDF because URDF is used in ROS. So maybe you can share with us a little bit. I'm not sure if you're using that because I'm not sure if I missed that part. It's the SDF, right?
Yes, SDF file, yes. It's the SDF file.
So maybe you can share with us a little bit about this SDF and also what are the difference in ROS and also in Gazebo, especially when we want to know more about or we want to simulate, for example, obstacle avoidance or collision, right?
Yep. I think the biggest difference the part on visual, let me just show you this one. I think in SDF and also in URDF, you have the link element. So one thing about URDF is if you are using SDF version 1.3 and above, I think the visual and collision part is actually similar for URDF and the SDF file. So as long as the collision is defined in your URDF file, you will be able to see the collision of the robot. So I just give you an example because in the file itself, in the example I provided, let me just do collision. If collision is actually enabled, you can see that the base itself is orange in color. But if you see this sensor over here is the interior sense camera is white in color, it's because the collision is actually not defined. So when you're actually working with navigation and things like that, this white color over here, it would not register as a collision point.
Okay.
So one thing about UIDFR is if you're familiar with SDF, the collision is written in a similar manner. So whatever you see over there can be applied over here also. Another thing is about shapes and sizes, different mesh itself. So for object that is irregular shape, I would suggest there's no way we can code ourselves in. There's so many points inside the collision in the mesh itself to describe the mesh. So most of the time, you can actually import the Collada file. So you can use the mesh actually generated by the Collada file as the input, you know. But make sure that because once you play with collision, you need to make sure the mass is correct also. Because when you actually have interaction of multiple objects, multiple free moving objects in the simulation, you need to make sure that the inertia and also the center of mass is correct. So if you can see from my screen over here, even with object of different shapes and things like that, usually like actually I did collision for the laser sensors, but I didn't do collision for the camera itself.
Okay.
So that's why you have collision for down here but not up there. So in Gazebo itself, this one I'm not 100% sure also. But whenever, even if you see over here, this is a sphere, you will notice that the inertia is always square.
Okay.
Always in cube form. So there might be some simplification in Gazebo. For this part, I'm still looking into it. You know, but it does approximate the inertia that of the particular object also with the collision shape itself.
Okay.
So with this itself, you can actually, you know, for example, this ball over here, as long as the collision is defined, you can use it for obstacle avoidance.
Okay.
So basically, that is the thing for the SDF. I think for the next part, when we are building the actor and environment, actually all of it are SDF file.
Oh, okay, right.
Yeah.
I see.
Yep.
Yeah, because I don't remember that I used any SDF for navigation because I'm not so sure because I'm using the TurtleBot package, so I don't really deal with the geometry or the object. But what concern that I need to know is about the inflation shape and for navigation, so which means we need to have some safety distance. So we actually inflate the body, and everything for us is 2D because we only concern on 2D navigation. So nothing much about the 3D shapes or the things because we don't really go into 3D navigation or 3D SLAM, which is if let's say you are doing with drone or anything SLAM, maybe you need a 3D SLAM. But for our case, that in my teams we only concern about the 2D plane, right? So over there, as long as we have big enough. Define big enough, I mean the robots, we can't actually make it larger than it is because like we need to make sure our robot can pass through the tight door, which is we cannot make the safety for object avoidance too big because like that will actually make our robot not able to pass through certain corridor or certain door. But I'm not sure if that is defined in SDF.
Yes, that is defined in SDF.
Okay, right.
The door itself and all those is actually, you can define it in the SDF.
Okay, right. Okay. So maybe I think like that is the things that you will explain in the next part, right?
Yes.
Okay.
Yeah. On the
Okay.
creating environment itself.
All right. So I'm not sure like should we go for another next question or you're going to proceed with the next session?
I would see any other questions from the
I'm not sure. Like if you don't have any question on your Google slide and I don't get any
my
message
slide.
over here. Yeah, but I think it's pretty interesting. And also one more things that maybe like the audience might ask is like actually how you actually get Coleda format file, because like it is not common and it is not
Yeah,
easily
yes.
generated by, for example, SolidWorks or any
Yes,
3D software. So because I think more common is the one that used for 3D printing, for example, like
STL.
STL and so
Yes,
on.
yes.
So do you have any things that you can share how to actually get this format, the file that in the format that is required, and you might want to share some experience that maybe you have
Yes.
worked with.
Maybe I can share with you on this because all the files that I get, for example, the laser model over here, is actually all in STL.
Yes.
So I actually use a website converter,
Okay.
STL to DAE.
Okay.
It's actually a free online converter. Let me just drag it over.
Yeah, so I guess that is a very important information for the audience.
This website over here.
Yeah.
Maybe I'll include this link in my slide also.
Yeah. Okay, you can
Yeah.
include this link on your slide and later on we can share the slide. Yep.
Yeah. So this is the STL to DAE converter. But one thing to take note is once it is converted, the unit is usually not suitable for Gazebo.
Okay.
So for example, the real sense over here, because STL file have the unit in mm,
Okay.
but
Millimeters.
once the converter actually takes it in, it will change the base unit to 1 meter.
Okay.
So
I think Ross is using meter.
yeah, Ross is using meter.
Okay.
So this one you have to open up the file and edit manually.
Okay.
But under asset there's a unit over here. So instead of 1, you need to put 0.001, then it will work.
So I guess that is a very important experience
Yes,
that you need to put in, because like it is not easy to detect this kind of error.
Yeah. We also actually when we first imported it, the camera is larger than our robot. So
Okay, right.
yeah. So that's why we have to actually go into the file and change the scale.
Well, I think like this is a
and
very
that.
important experience that people can learn from what you can share here over here.
Yeah.
Right.
I should put this into the slide.
Okay, right.
So hope that actually will help a lot of people, especially in importing the different size and different shapes.
So are you using I'm not sure, like SolidWorks or Blender or anything to create your shape? For example, if you want, like for example the wheel, or you just draw within the gazebo? We
actually use SolidWorks to create some of it.
Okay.
I can share with you the view because I will share it in the section later.
Okay.
We actually created the map of the university.
Oh, all right.
I can't share you the code for the.
So how you scan it, or how you actually get the map? I'm not sure it's a 2D map or it's a 2D scan or a 3D scan.
We are not doing it from scanning. I actually have one student actually build the whole environment.
You mean like it draw? It measure everything and draw it out?
Draw, and also we take pictures and all those, so that we have all the signage and all those.
Okay, so that is amazing work, I can say.
Yeah, I'll share that.
Okay.
I'll show you the screen, but I can't share the source code.
Yeah. I mean, like, yes, you can share anything that people. I mean, like later on, our audience can refer.
Yes.
Yep.
Yep. So any other question? If not, we can proceed to the next part of it.
Yep. Yeah, I think like yeah, you can proceed like continue from what you just said.
Yep.
Yep.
Okay, so let me just continue with it because
Okay,
the next
so
part is to create your own environment. Let me just stop the. Let me just pick from this gazebo first. It actually takes some time for it to stop.
okay, right. So I excuse
Now,
myself and let you continue with your second
yeah,
part.
sure.
Yep.
Okay. So the next part is to actually create what we call a scene and also the actors in the environment itself. Because if our robot is operating on the empty world, there's nothing much we can do in that particular environment. So what we have over here is we actually create a world. But one thing is there are already a lot of models out there that we can use. So not everything you have to actually create on your own. But there are some that you really need to create on your own, then you have to do it. But if not, you can actually refer to this one. This is the Open Robotics Gazebo repository. So, my Gazebo is still loading. You can actually get this clone this and get access to quite a number of different objects itself. So this is where I've cloned it. So for example, if you are building your own room, for example, you can input things like, let me see, what will you find in your room? A coffee table maybe, and you might, let me see, what else in your room? Okay. There's not much things for your room. But anyhow, you can actually get a lot of pre-render, pre-built objects that you can use. But one thing, they also have pre-built environment that you can use. So, for example, okay, some issue on Gazebo itself. Let me just restart the Gazebo. Hi, I think my call dropped off just now. So, can everyone hear me now? Okay, I got dropped off just now. Yep. Okay. Yep. So let me just turn on Gazebo. I think okay. where am I just now? Okay, Gazebo models. You actually have a lot of pre-built environment in this for Gazebo itself from the repository. Actually, you even have a past RoboCup competition field. So these are previous RoboCup competition field. Like for example, if you have things like you have school, for example, you can actually have, oh, this is only an outer building. Internally, it's actually empty. So you can see that, inside is empty. So you have a school over here. You can also have things which are not empty in the middle. So for example, I have a cafe over here. So let me just clear off the Gazebo first. One thing about running simulation is you need to make sure your PC is actually strong enough for it to render all everything that's available there. If not, it does slow down your PC quite a bit. I'm actually running on, I'm having a ThinkPad workstation over here, and sometimes it still feels laggy for my PC. So make sure you have sufficiently strong computer for it to run your simulation. So for example, here you have the cafe. So with this repository itself, you can actually build quite a number of things you need for the simulation. So for example, you have a cafe, you can have your cafe table inside. Then once you're done with it, you can actually save your work. So once you save your work, it will actually generate all the files that's needed, link it to the location. And with this, you can actually build any environment that's needed for example, if you're working on your own robotic project, you can actually use this. Even if you are doing for like at home competition, depending on the requirement, you can actually build a room based on this. But if you are not, you don't want to use the object over here, let me just start up with a new world again, empty one. You can also build, I would say, the whole environment yourself. So let me start another Gazebo. Because there is an online database that you can connect to, but sometimes it's a bit laggy from my side. So let me share with you, like you can actually create your own building itself if you want. So you can create walls, so if you see from here, I've already created a room itself. Then you can use the materials that you see in like for example in the the Gazebo repository just now. You can actually like put furnitures inside, put bookshelf inside, and you can actually add texture to the wall itself. You can actually, if you want to go like 2 floors, you can actually add stairs Yeah. So you can also add doors, windows. So if you notice, it's just like a, you know, floor plan tool itself. And what you build can be quite complicated. So let me just share this one. We actually have this build. On Gazebo is loading. So this is actually our university, one floor of our university where we usually test our robot. So if you notice, we actually spawn our robot in the middle, and we have the university environment over here. We still haven't added the tables and chairs. So, but this middle area is where we actually test our robot usually, and you know, we have all the labs over here. If you notice, all these doors over here are doors that you can interact with. The robot can actually interact with the door itself. So this actually takes quite some time for us to actually build. But if you notice, you can build complicated environments using the tools. So yeah, these are the notice board that we have in the floor also. So we actually take photos, we take the environment, and we actually place all these things in. So this actually help us with some of our project itself, where we try to build a service robot for you know, for the particular floor itself, where, you know, the robot can look at signs and, you know, try to interpret where to go and how to go. So this is one of the.
Danny, sorry. Can I ask one question about this model? I mean, like, how about the measurement? Is it like
we actually
consistent with the real measurement? Really?
Yes.
Oh, okay. Yes. So your students actually measure first before they draw?
This one we can. This for our university itself. We can get the floor plan.
Oh, okay.
That's why I can't release this out to the public.
I see. Okay. So they draw according to the floor.
Yes, according to
floor
plan. Yes.
Oh.
Like what you see just now, the example where I built the room itself. So you can actually draw it according to the floor plan.
Okay.
Yeah. So, but
there's no measurement display like when you draw, right?
There is.
Oh, there is. Okay.
Yeah,
Okay.
Yeah.
Nice.
So, but I can't share this out to
yeah, of course.
because it is exact measurement of our university.
Yeah. All right, thank you.
Yeah. So these are the scenes that you can create. So if you are working on you know, robots, you can create, you know, your house. You can create you know, a bedroom. You just need to put in the correct, you know, models. If it's not available, you can actually like generate using SolidWorks. Might be a bit hard, but I would recommend you to go to website like grabcat.com, where they actually have a lot of open source free model that you can use, and you can actually import it as part of the scene for your simulation itself. So okay, I think that is for the scene itself. So this one is remember the cafe scene just now? I created, you know, the robot over here. You know, I placed the robot, I launched it with the world that we have created. So now, next thing is actually human. So once we have created the scene itself, we can actually run our simulation there. So let me just show you another one. So once we have created the scene, we can actually put our robot inside it. So let me just launch an example. So make sure you have a strong PC, because even in my workstation, it takes around 30 seconds to start up. So now, for the example over here, we have a robot. So this is a robot that we created just now. In this example, we actually I've actually launched a SLAM toolbox over here. You can see a camera, but I'm only using laser-based SLAM. I did not include vision SLAM in this example itself. So let me just turn on the graph. So once you have built the environment itself, you can see that your robot can interact with the environment. So I'm using a SLAM toolbox for SLAM, and when I drive it around, I can use the scan to create the map over here. So if I drive it around, oops, driving too fast. So you can see that in the view itself, I can actually see the environment, the depth measurement for the environment, and when I'm driving around, I'm able to build the map of the surrounding. So you can drive it through looking at iris, or actually drive it looking at the real environment itself. So all the environment, if you are using model from the what we call it, the Gazebo repository, all of them are SDF file, and all of the models over here are the Collada texture file. So like what Jeffrey stated just now, is you can actually have all the collision data over there. That's why when you do navigation and when you use depth camera, you can actually see the depth points, from the model itself. So you won't lose any information. You won't get transparent object in a sense. So this way you can actually drive it around, move it around. I think you can run some of the example in the open Courseware using this robot setup also. So once you can move around, you can see. Now, next thing is actually human actor. So to add human, again, use the human actor is a bit harder to control, because in Gazebo itself, you can actually animate the human itself. But up until now, what we do is we usually use the pre-existing model from the Gazebo repository. Again, the repository is here. They have a few, like a human standing, human sitting, human walking. They also have one where the human is moonwalking. So if you, for this example over here that I share, I will use the script to do the animation. So inside the world itself, I actually have the script to do animation of a walking model. So if you need to combine a few animation, for example, you want a person to stand, and then after standing, start walking. So you need to write your own code for it using their API through C++. But if you only need to, simulate one item, for example, only walking without changing to another animation, you can use the script directly. So once you have added the human in, you will see the human walking over here. Now, last example for the day is I will run a simple follow example. So let me just stop the previous simulation first. So this code was developed quite some times ago when our robot don't have a depth camera. We actually only have a laser. So we actually use the laser to track and follow the nearest block actually. So it's not the follower, I'll just iterate first, this is not the follower program that we use in the competition, because in the competition we actually use the vision-based system to do the following. This is just a very example that we use the laser data to actually do it. So let me just launch the simulation itself. So this is a pre-map environment that we have. So as you can see, this is the robot itself. I have a very slowly walking human over there. So you can see the laser actually detected the first block over here, the human leg. So the robot will actually track it and follow it using a simple PID loop itself. You can see the animation is running over here, and then the robot is following over here. So for this basic example, the human will actually teleport at the end, because we actually need to define where the human is walking to. So, and also what speed that the human is walking towards. So, as you can see over here, we have like the walking model itself from the repository. Then at time 0, it is walking at, it's starting at 0 position. This is the angle that the person is facing. So it will walk, you know, at time 50 seconds, it will reach, you know, -1 meter. Then at time 100 second, it will reach -4. Then at 150, it will reach -6. But this script will work in a loop. So after at 150 second, the human will actually teleport back to the 0, 0 position. So, okay. So after 2 minutes, 2.5 minutes, you can see the person teleported back to the origin location. So basically, with the data sets that you can get, the public data sets you can get out there, you should be able to create, you know, simulations for tasks that is needed in the RoboCup, you know, competition itself. So doing this also, it does speed up your work in simulation. It also does speed up your work in the real robot also, because you can actually test out a lot of different algorithms or different you know, things that you want to try in simulation before going to a real robot. But do keep in mind, if you work on real robot, sometimes there are a lot more quirks to work out in a real robot itself. So basically, I think that is what I would like to cover for the sharing. I've also posted this project over here that contains all the examples that I want to share. So you can actually get it from this GitLab link itself. So basically that covers everything that I would like to share today. Any question from the floor?
All right, so thanks, Danny. Thanks for the very nice sharing. I think like I can see a lot of in-depth about, because I never actually really worked on Gazebo and on simulation, because previously I involved in SigVerge and using another system. Yeah, maybe you can put your screen there, because like maybe I have some script question that regarding that, maybe you want to show your screen. Okay, so while waiting for question from the floor, if let's say there is any, so maybe I can start by asking you some question that maybe the audience might be interested. So personally, I have few inquiry that I would like to discuss with you. So the first thing is like, actually I don't know that much about, you can actually put the actors and also you can get the API to make it, to animate it. I'm not sure like how flexible it can go, but based on your understanding on that, is it possible that we can actually get the view from the eye of the person, and also we can actually control all the body joint of that actor? Is that possible?
Individual joints of the through the C++ API. Then for the view of the from the person to that is actually through adding a camera on the actor itself.
Okay.
Right. But I think Gazebo itself have a multiple view. But I have not tried that before.
Okay, right. So the reason of my question is because I have, previously I involved in SIGVERGE project, which is, I'm not sure if you're familiar with that. So SIGVERGE project is actually another system. They try to use, what is that system? Unity, right? To use the Unity system to create a virtual environment and also to interact and also to connect with ROS in order to create simulation for at home. So that was the idea previously. And then until I saw your presentation today, that maybe we can actually do the same thing with Gazebo. So that's why I would like to know more that how possible we can actually use this Gazebo to do something that previously we planned to do. For example, if we can get the view, which is very possible, I think you just add a camera on top of the human actor, because I will assume the human actor is very similar like another robot.
The only thing is Gazebo, they run the animation. They are not like SIGVERGE, because SIGVERGE you are running on a gaming engine. We use SIGVERGE also.
Okay.
Because we are supposed to go for the
WRS, right?
WRS, yes.
Okay, correct.
Yeah. So Unity actually provide you a more flexibility when you are controlling the human skeleton compared to Gazebo, because there is an API for you to control the skeleton in Gazebo. But personally, I have not used the API except for stitching animation.
Okay.
So what they have is actually simpler for Gazebo if you have pre-render animation. Like the walking is actually a pre-render animation, and you are giving position to position, and they can interpolate the animation. Like for example, you walk faster, you walk slower. But to control exact skeleton, it will take quite a lot of work compared to Unity.
Okay, alright. So because I think like Unity already pre-built that. For example, you can connect to, for example, OpenPose or whatever. That you can straight away stream all the joint position and straight away control. But in Gazebo, maybe you don't have all this.
In Gazebo.
Yeah, you don't have all this thing, and you need to build the thing.
I'm not sure any third-party package or anything. I have not explored on that side.
Yeah, because like always we want to do is, for example, like at home, we actually have some human-robot interaction. Okay. So in order to simulate those kind of human-robot interaction, we always try to find what tools we can use. For example, if we can get the vision, so the view of the human, we can actually input into our VR devices that we can think of, for example, HTC or Oculus. Then the human in real world can actually interact with the virtual environment and also the virtual robots. And including if we can get the movement of the human. So I think that is what we want to achieve in SIGVERGE, and they're already like doing a lot of job on that. Okay, so that is what the Sigverse project is currently working on to simulate the human robot interaction. But I was like not sure, like as you have explained, so which mean Unity is actually better in this sense, right? Because like you have more resources and all the thing. But the problem is Unity environment and all the tools, and also Gazebo and all these things, they are two different sets of tools that we can use. So which one is better is maybe like very subjective, but from your standpoint of view, I understand that maybe Unity will have more resources to do this kind of simulation. Although I'm not sure how good is the integration between ROS to Unity and also ROS to Gazebo, because like I assume ROS to Gazebo will have better integration.
I think the integration from ROS to Gazebo is more lightweight because when we run the Unity setup that we have, we actually need we actually run it on a much better PC than what I'm having now. And even with that, our simulation is still laggy.
Okay.
For our case, but I think in terms of packages and things like that with Sigverse itself, I don't see a very big difference. But on the other side, Unity does have a better control of the 3D world compared to Gazebo through Sigverse. Yeah, that is one, I would say, one advantages of using that. But if there's not much direct input, or you have means that there's not much human robot interaction, actually Gazebo would be a better choice in my opinion, because it's actually much tightly integrated with ROS itself. So there are much more libraries and plugins that you can use directly, especially for sensors and all those.
Yeah. So which means like if pure robot simulation, then Gazebo will be a better choice, right?
Yes.
Okay, but human robot interaction, then maybe you need to see like maybe Unity give you actually more control on the scene and also on the human. Okay, so the next question is not just the actor, but just how you say we can interact with the objects. For example, the door.
Yes.
How far we can actually interact with, or do you have any example we can interact with the objects in the scene?
I don't have it right now, but what we did previously was we actually have a block on the table itself where we can use the robotic arm to grip. So that is only a cylinder that we put inside, and we can actually use the arm to actually grip the object. But
how realistic, or how to say, the fidelity of the grabs itself, because like
it depends on the Gazebo parameter you use. Actually in Gazebo itself, you need to key in the friction parameter of the material. Let me just show you this. It's available in SDF file and also URDF file. So when you define your, for example, when you define your robot views, let me just go to robot views. There is the surface friction. So there's a mu1, mu2, the contact surface, if you can see in my screen, and there's also KP. This is deformation. Like when you touch the thing, how much it will bounce back and things like that. So if you actually put in the correct material property, you should be able to get back the correct response from the simulation.
Okay, something maybe is quite a stupid question. Like, do you know what is the dynamic engine of Gazebo?
Oh, this one I'm not sure.
Okay, right. Okay, maybe you can check, but I think the dynamic engine will determine how good we can do the simulation in the particular system, I guess.
Yes.
Yeah, because I think, because in my team we actually have manipulation, and currently what we are doing is we focus more on using the tool in Move It. to do the grabs and all these things. But for at home, especially like service robot, we concern more on, for example, open the door. And also like open the cabinet, for example, the cabinet door or the drawer, and in order to do some tidying or sorting tasks. So these are the how to say, robot to object interaction that usually we have. And also like for objects, we do pick and place and so on. So these are the things that I think we concern in at home, especially in our challenge, which is I'm not sure how far we can go with the simulation. Okay, but that actually links to my next question is, do you actually verify your simulation with real robot before?
On our developed robot itself.
Yes.
Our own one, yeah.
Yes.
We try it with the base only, without the top extension, because we are still building the top extension in simulation.
Okay, right. So what you have done and what result you actually obtained?
Mainly is the simulation in, remember the UTAR, the floor that I showed? We actually tried to verify our simulated robot. We actually run the explore algorithm to see it in the real world and in the robot itself, to see whether we can match the data and everything.
Okay.
With that also, actually we did some tuning on the weight parameters.
So what you study over there is actually more on navigation, right?
Yes, more on navigation at this point.
Okay, so because like previously also when I work with our sponsor like Jupiter Robots, they actually create the same thing like the environment in their office, and then we do the navigation. And the accuracy of the navigation, for example, we use the navigation, the G mapping and AMCL is quite acceptable. I mean like, is within the acceptable level for service robot application, because it really stopped at, for example, in front of the table or in front of the chair with quite very accurate the orientation. So it's very acceptable even for our application. But of course not as accurate as what the industrial needs, but for service robot application, I think that is actually very acceptable.
Yep.
Yeah, so I guess you are doing the same thing, but you actually have a much bigger a map, because like you actually like draw the whole,
yes, the whole floor,
the whole thing. So but that also I think is not considered too big, because like when we are running navigation for a very big environment, for example like an area, not just a floor or a room, but an area. So maybe the G mapping and also the MCL might have a lot of how to say, the accuracy might be not up to the acceptable level for example like you have a map that is more than 1 km and so on.
Yeah, I think for the size itself, I'm actually having issue with GM mapping. That's why I'm using the SLAM toolbox.
Okay.
Yeah, they have their own. You can actually run multiple times and do the map closure yourself. They have multiple matching. So the SLAM toolbox actually cover that for us.
I'm not sure like what are the advantages when you're using this SLAM toolbox, because like I heard like people that not using the G mapping and the MCL, they are using, for example, like Hector SLAM.
Hector SLAM, cartographer, we have tried before.
I think Hector SLAM is more for those outdoor mapping.
Yes.
Yeah, because like Hector SLAM actually help you to correct the, how to say, the incremental error, which is G mapping actually don't help you. Like when you will create a loop, a closure, the map actually like, how to say, not closing.
Yeah.
Right, so which means
that's the issue with if we map for the whole area that you see in the simulation just now.
Yeah, because like when you it actually add up all the incremental error, and eventually like when you make a loop or a closure, it actually don't match with the original point. Right. Yep. But do you find very useful for this simulation platform in your actual robot development?
I think mainly is because we are working in a team, and we actually only have one robot. Okay. So I mean, when everyone need to work on the robot itself, like for example, some need to work with the vision system, some need to work with the location tasks, some need to work with the arm itself. Then it does help with the development when we actually only have one physical robot.
So do you mean like when you build the simulation model, you can actually divide the task? For example, like someone actually work on the vision, someone work on the things, and then you can put all the things together to do the simulation. Okay, so that is what you do with the simulation development, right? Is there, I'm not sure like if you can share with us like in more detail about what kind of research work that you actually work on with the system that you have developed.
I think because currently working with a master student that's working on the machine vision algorithm, but it's more towards the optimization of there's one part where you actually do optimization when you do machine learning. It's more towards the algorithm there. So the simulation is more towards the showcase of the application of the machine vision rather than the research itself. So like one of my master students, he's working on the solver itself. So that is the research work, but we at the end we apply on the robot itself, on the output level.
Okay, because in my team, I can share with you like for vision system, we actually use some SigVerge previously for our research in the case that we want to see the same algorithm in different environment. So simulation can actually give us the advantage that we can do a lot of experiment in different environment, because in real world we cannot do that. We cannot provide a lot of environment with different setting, different lighting condition, different object, different layout, and so on to do the experiment. But simulation actually can help us with that.
Does help.
So it actually, for example, like you can use the scene, the previous scene, and put in and see how the robot behave. But I understand that for vision system, we do a lot of recognition that we need real pictures. Real object. Because just now you actually show us the sign or whatever that you do. So I'm not sure, like, do you actually do the recognition of the sign in simulation as well?
We do the recognition of sign in simulation.
Oh, okay. But I'm not sure, like, how do you verify that with the real world, the real application?
The main thing over here is the recognition of sign and also the OCR for the characters on top.
Okay.
We have tried. The student actually developed the algorithm on simulation. Then we tried using our robot in the. But I think our university is a very well controlled and well lighted, well controlled. So the it can actually pick up the characters and it knows where the sign is.
I think like it is quite an interesting topic for student development research, and even like for Cyborg, actually a lot of time Cyborg we look at characters, we look at sign, which is very similar in simulation and in real world, because we are not looking at very complicated organic pictures to find things. So I think that is also in some degree that I think is acceptable in terms of like Cyborg, because I think in particularly, for example, in service robot application, it is quite important. For example, you ask the robot to go and find someone in some room. So if let's say you can actually read the sign and you can actually see the name, because just now I saw you have the number plate. Sorry, not number plate, but name plate.
The name of the labs.
Yes. So if let's say that is proven to be working on simulation, and I think some degree of chances that it will success in real world as well. So which means I think that is good. For example, like you can do a lot of test data, you can get a lot of test data in simulation in that sense. Right. So it's a very nice discussion today, and I think like I actually learned a lot, because I never really worked on simulation, but I learned a lot on your sharing today. I'm not sure, like, is there any other question that we can discuss? We have about 5 minutes before 5, so we can use up all the time for the discussion. Any final things that you would like to tell the audience?
I think one thing is when we work on simulation, also this is what we found out. They are always different in the real environment. I think some of the issues that you raised, like lighting and all those, does affect, because in the simulation itself, it is actually perfect. You know, even though it doesn't show on the simulation, sometimes when we run the real robot, there are glares and all those on the signage itself. That is when we fail to recognize in the real world.
I see. All right. But that's the other issue, right?
Yeah, other issues. So, but one thing, if you are building your own robot in simulation, I think the few things that I shared just now are very important, especially on the inertia and also collision.
Okay.
When we just started, you know, we did not pay much attention on the inertia and collision itself. It actually causes the robot to flip or to actually behave in a weird way.
Oh, okay, right. So you mean like inertia is like it don't tally with the speed, so your distance calculation might be not correct or something like that.
It's actually your weight and weight distribution of the robot doesn't tally. So
Okay.
When you move, your robot might flip over, or your robot might.
Okay,
bounce,
all right.
you know?
Okay, right. I see,
Yeah.
I see. Right. So I think that is interesting to validate your model
Yeah.
even before you do any application development.
Yes.
Yeah, because I actually have one student that previously worked on building the model for wheelchair. So we actually have one project on that, and that student actually spent a lot of times to correct the model until we can get the navigation tally with the real world.
Yeah. Actually, MATLAB helped a lot.
Oh, you use
usually-
MATLAB for this?
No, not MATLAB. MATLAB.
MATLAB, okay, right.
Yeah, one that calculates the inertia for you.
So it's quite accurate from your
Yes,
experience?
it's quite accurate, but you need to scale it correctly. There's a
I see.
scaling issue also, because all of them actually uses 1 mm
Okay.
as the unit, because every MATLAB is actually unitless.
Mm-hmm.
So, but it's 1 unit, so you need to scale it accordingly because you know, Gazebo is using 1 mm.
Okay, right. Because in our team we always use like standard platform or platform that's open source that we can easily available commercially. So we actually don't have much experience in building our customized robot platform on this. So I don't have much experience on that. So it's very glad today that you can share with us how you actually build your customized platform in real world and then do the simulation model in Gazebo. So I think this is a very important development, and also I think like a lot of our audience, and also maybe later on people that found this video might find it very useful for their development. So
Yeah.
thanks a lot for your sharing today. And then I guess the time is almost out.
Yep.
Okay, so we would like to close this session, but I would like to discuss more things after this with you. So maybe you can stay online.
Yeah,
And
sure.
let
Okay,
me.
thank you, Danny.
Yeah.
Alright, thanks, Jeffrey.
Okay,
Bye.
Thanks. So I will let me how to say conclude this session. So maybe Danny, you can pass the how to say the screen for me. Okay, so let me back to this. Is it back? Right. Okay. So yeah. So thanks everyone for joining today's session, and thanks Danny for the very interesting and very excellent presentation, and also demo that you actually show us the actual things that you have developed, and also very nice sharing in terms of a lot of tips that how to build the model, and also the real how to say the tools that a lot of people are actually looking for example, how to build a model and so on. So I think these are very valuable knowledge that we can share, and yeah, I'm glad that I have this video. So I hope this video will be viewed a lot later on for particularly for people that want to develop their customized robot base and simulate in Gazebo. Okay, so for all of you, thanks a lot for joining, and I list down all these links. So if you want to find our information, I don't know how to get rid. Okay, so let me get rid of the panel. Okay, so you can refer to our website for more information. For example, like after this session, we will upload the YouTube video and also all the links and also all the resources that Danny is going to open source. We are going to put up on our website, so you can refer to our website later on to find all those resources. And once again, please join our Facebook page if you want to like communicate with our community. And also all our open source materials, particularly on the source code, we have it on our GitHub, so you can find the ROS version or the MATLAB version and also other different platforms. And yeah, online classroom, so this is a link that you can find those learning resources. And finally, if you have other things that you would like to contact us, the last one is our email that you can contact us directly for any matters that you would like to discuss with us, right? So as a final note, so I would like to over here remind you that we have a few more, okay, this kind of this special online challenge 2020 invited lecture series is scheduled for the coming week and also month. So please take note, and also if you're interested, yeah, feel free to sign up. You can scan the QR code to get to the registration page, right? So with that, I would like to close the session today, and thanks Danny for the very nice sharing, and thanks for all of you for joining of today's session. Thanks a lot. Right, see you.
Thank you.